Welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So in this class, we'll discuss about the polarization, which is one of the most difficult topic for most of the students. What is the polarization of the antenna? So basically, if you consider an antenna is placed at the origin of the spherical coordinate system, and assume that this antenna is radiating fields in all directions. So now, somewhere in a far away distance from the antenna, we call it far field region of the antenna, you can represent the electric field of such antenna in terms of its theta and phi components. So electric field in the far field can be expressed in terms of theta component E theta and E phi component E phi. So now if you put the time dependence here, so the previous expression we have was space dependent. If we put into the time dependence in the previous expression, then we can express electric field as a function of theta phi and t as E theta cosine of omega t theta hat and E phi cosine of omega t plus delta phi hat. So now here you can see that there is one extra term here, delta here. Delta is the phase difference between your elevation and azimuthal components of the electric field. If your E theta and E phi are not of same phase, that same phase difference is denoted by delta here. So how do you define the polarization? Polarization is defined for the electromagnetic waves as you look at the tip of the electric field at a fixed distance. How is the behavior of the tip of the electric field? Based on that, we can define polarization. So antenna polarization basically means that you look at the field which is radiated from the antenna in the far field and find out its polarization of that wave which has been radiated from the antenna. So now let's consider the simplest case, which is called the linearly polarized wave or linearly polarized antenna. So we're looking at the fields which has been radiated from the antenna in the far field. For the linearly polarized case, there won't be any difference between the phase between E theta and E phi component. So delta is 0. In that case, the total electric field will have E theta cosine of omega t theta hat plus E phi cosine of omega t theta hat. So this will be phi hat here. So now these two components, they are in the same phase. So now if you want to find out what is the angle this total electric field is making with the theta axis, you can find out that is theta LP for the linear polarized wave should be equal to tan inverse of phi component of the electric field divided by the theta component of the electric field. So now this cosine omega t is same, so it cancels out. What you get is tan inverse of E phi divided by E theta. So this is the angle total electric field is making with the theta axis. So this diagram will actually show you what is linearly polarized wave. It will be illustrated from this diagram. So here we are showing some electric field. So wave is propagating along this direction. We have transversal electric field and transversal magnetic field. That means this electric field and magnetic field are perpendicular to the direction of wave propagation. So now in this case, electric field is a cosine omega t, so with time it should be reducing. Cos of 0 is 1, cos of pi by 2 is 0. So the amplitude of the cosine function will vary like this. This is the electric field. The black lines are for the electric field. Look at this tip of the electric field, with respect to time. For example, you look at one fixed point here. This tip of the electric field will be always confined in this one line here. So this tip of the electric field, when you look at one particular point, this is the wave which is propagating along this direction. So the wave is incoming towards this direction. You stand here and look at the wave. So the electric field vector will be always confined in this line here. So that's why it's called linearly polarized wave. You look at the magnetic field also. Magnetic field will be also automatically confined in one line along this. So for linearly polarized wave, electric field is confined in one line. The tip of the electric field traces out a line. That's why it's called linearly polarized wave. We can also consider another case which is called circularly polarized antenna, or the wave radiated from the antenna is circularly polarized. In that case, delta will become either plus minus pi by 2. That means there will be either phase lead of pi by 2 or phase lag of pi by 2 of the phi component with respect to the theta component. And one more condition for circular polarization is that E theta and E phi component will be equal. They will be of same amplitude. So in that case, E theta is equal to E phi, let's say, is equal to E0. So in that case, you can express the total electric field as E theta cosine of omega t and E phi cosine of omega t plus pi by 2. Delta becomes either plus or minus pi by 2. So the total electric field will be E theta cosine of omega t theta hat minus plus E phi sine omega t theta hat, because you know cos of omega t plus pi by 2 is simply minus plus sine of omega t. So now if you look at the angle this total electric field max with the theta axis, you can find out. So theta Cp for the circular polarized will be equal to tan inverse of this component divided by this component. So in that case, you get minus plus sine omega t by cos omega t, because I know that E theta and E phi is equal for the circular polarized wave. So when you take tan inverse of minus plus tan of omega t, what you are getting is minus plus omega t. So when delta becomes plus pi by 2, what we are observing is that the angle is negative, and when delta becomes minus pi by 2, angle is positive. And one more thing is that this angle, this total electric field max with the theta axis is changing with respect to time. At time t is equal to 0, the angle is 0 with respect to theta axis. Then at other values of time t, it will be forming a circle, no, in positive direction, or let's say anti-clockwise direction. So that's why we have right hand circular polarized wave. When we have delta is equal to minus pi by 2, okay, when delta is equal to plus pi by 2, the angle is negative. That means the rotation of this angle with respect to time will be in the clockwise direction, in this direction, clockwise direction. And when delta is minus pi by 2, so this angle is positive. So with respect to time, this angle will be rotating in the anti-clockwise direction. So now if the angle is rotating in the anti-clockwise direction, we have a right hand circular polarized wave. Or if the angle is rotating in the negative clockwise direction or anti-clockwise direction, in the clockwise direction, then we have a left hand circular polarized wave. So negative is for the left hand circular polarized wave, positive is for the right hand circular polarized wave, and delta for that particular case will be either plus minus pi by 2. So when delta is equal to pi by 2, we have a left hand circular polarized wave because this angle is negative, and delta is minus pi by 2, this is plus omega t, so we have right hand circular polarized wave. So this diagram will show you what is a CP wave. So let's look at the wave which has been released from an antenna which is circular polarized. When you look at the wave, so now this wave is no longer in one particular direction, no? It keeps on rotating. So this wave is rotating, then it's coming back. So basically when you look at this wave in the far field of the antenna, this wave is actually tip of the electric field of this wave is forming a circle. So it's forming a circle. The tip of the electric field, if you look at it at a fixed point in the far field of the antenna, it's forming a circle. That's why it's called circular polarized wave. Depending on whether the tip of the electric field is moving in anti-clockwise or clockwise direction, you will have right hand circular polarized wave and left hand circular polarized wave. There is another alternate form of expression for the total electric field vector. You basically take real part of E0 exponential j omega t theta hat plus E0 exponential j omega t plus pi by 2 phi hat. So when you take real part of that, you will be getting the previous expression you have for the electric field. So let's consider right hand circular polarized wave. In that case, we have a minus pi by 2 here. This is the expression you have here. So now if you take out E0 exponential j omega t common, what you have here inside the second bracket will be theta hat plus exponential minus j pi by 2 phi hat. So the expression for the total electric field for the right hand circular polarized wave can be expressed as real part of E0 exponential j omega t theta hat minus j phi hat. You know that exponential of minus j pi by 2 is equal to minus j. Similarly, for left hand circular polarized wave, this will become plus here. In that case, the expression you have for the, this should be plus here, expression you have for the electric field will be real part of E naught exponential j omega t theta hat plus j phi hat. So the total electric field in the CP wave we have already found out. So now what you can observe is that for unit vectors for right hand circular polarized wave, unit vector would be of the form 1 by square root of 2 x minus jy. If we consider basically, let's look at the CP antennas from a different perspective. So here what we have looked was CP antenna has component along theta and phi direction. Let's say you consider another CP wave in which the motion of the wave is along the z-axis, then your electric field will be confined perpendicular to that, so it will be in the xy plane. So electric field will have x component and y component in that case for the wave which is propagating along the z-axis. So now the x component of the electric field can be expressed as E0 exponential j omega t x hat. Y component can be expressed as E0 exponential j omega t plus minus pi by 2 y hat. So in this case, the amplitude of the x component and y component are equal, and we have a phase shift of plus minus pi by 2. So we'll have a circular polarized wave. For our RICP, this will become minus pi by 2. In that case, your expression for electric field will become exponential E0 exponential real part of E0 exponential j omega t x hat minus j y hat. Similarly, if you consider for the left hand circular polarized wave, expression for the electric field will become E vector will become real part of E0 exponential j omega t x hat plus j y hat, because here for the left hand circular polarized wave this will become exponential j pi by 2. Exponential j pi by 2 will become plus j here. So you can find out the unit vectors for right hand circular polarized wave would be of the form 1 by root 2 x hat minus j y hat, and for the LHCP wave unit vector will be of the form 1 by root 2 x hat plus j y hat. So this expression will be using it later on. So another more generalized case for the polarization is called elliptically polarized wave. In the elliptical polarized wave, E theta and E phi would not be equal, and delta should not also be equal to 0 or pi, or delta should not also be equal to plus minus pi by 2 also. Those cases are for the circular polarized wave and the linear polarized wave. So now the total electric field for the elliptically polarized wave can be expressed as theta component of the field plus a time exponential j delta pi hat exponential minus j beta r exponential j omega t. So exponential j omega t is for the time harmonic fields, exponential minus j beta r is for the wave which is propagating radially outward, and we have a transversal component of the electric field elliptically polarized. The amplitude for the theta component we take 1, then amplitude for the phi component will be a. So a and 1 are not equal, so these two amplitude will not be equal. And we also has a phase shift of theta and phi component. That phase shift is denoted by exponential j delta. If delta is equal to 0 or pi, it becomes linear polarized wave. If delta is equal to plus minus pi by 2 and a becomes 1, then we have a circular polarized wave. So circular polarized wave and linear polarized wave are particular case of the elliptically polarized wave. So now you can also find unit vector for elliptically polarized wave would be theta hat plus a exponential j delta phi hat divided by square root of 1 plus a square. We have a term square root of 1 plus a square, so that amplitude of this vector should be 1. So how do I decide whether it's a left hand elliptically polarized wave or right hand elliptically polarized wave? If you express your total electric field of this form, the delta would be able to tell you whether you are having a left hand elliptically polarized wave or right hand elliptically polarized wave. If delta is in the upper half plane, that means you have xyz plane, or let's say r theta phi plane, or let's say you consider theta and phi plane here. If you have a theta and phi plane, and if your delta is in the upper half plane, we have 4 quadrants, no? 4 quadrants in the theta and phi plane. So If delta is in the first and second quadrant or in the upper half plane, then you have a left hand elliptically polarized wave. If your delta is in the lower half plane or in the third and fourth quadrant, then you have a right hand elliptically polarized wave. So now in this case, when you have elliptically polarized wave, it will have minor axis and major axis. The ratio of the major axis to the minor axis is called the axial ratio. And if you have axial ratio is equal to 0 dB, that means your major and minor axis are of equal length, then we have a circular polarized wave. If your minor axis is tending to 0, in that case axial ratio becomes infinity, you have a linearly polarized wave. So this diagram will show you that if you look at the wave is propagating along this direction in the far field of the antenna, and you look at the tip of the electric field, the tip of the electric field will be making a ellipse. So in this case, this looks like a major axis, this looks like a minor axis. Ratio of these two is called the axial ratio. So in order to define the bandwidth of the CP antenna, we actually use axial ratio as a parameter. If axial ratio is less than 3 dB, we call it circular polarized wave. We'll look into those details later on if it is necessary. So let us summarize. For antenna polarization, look at the radiated wave from the antenna in the far field region of the antenna, and look at the tip of the electric field. The curve that tip of the electric field trace out, if it is a line, then you have a linearly polarized wave. It is a circle, then it is a circular polarized wave. If it is a ellipse, then it is a elliptically polarized wave, or elliptically polarized antenna, or circular polarized antenna, or linear polarized antenna. So now there is something we need to know when we have a transmitting antenna and receiving antenna. Depending on the polarization, the amount of signal you receive at the receiver would be different, no? So there is something called polarization efficiency. So let us assume that there is a transmitting antenna and it's giving a maximum amplitude of EM, and the polarization of the antenna, unit vector for the polarization of antenna is given by ET here, ET hat here. ET hat is a unit vector which gives the polarization of the transmitting antenna. Similarly, you also assume that in the far field of this antenna there is another antenna which is receiving the signal from the transmitted antenna, and the maximum magnitude of the field which this antenna can receive is given by EM, and the polarization of this antenna is given by ER hat, is the unit vector which gives the polarization of the receiving antenna. So now we have a term which is called polarization efficiency. So polarization efficiency is basically defined as dot product of polarization unit vector for the transmitting antenna and complex conjugate of the polarization unit vector for the receiving antenna. You take amplitude of that, square of that, you get the polarization efficiency. So let us see many cases. Let's say you have a transmitting antenna which is also linearly polarized, and receiving antenna also linearly polarized, but only thing is that the orientation of the antenna for the transmitting antenna and receiving antenna is different. So let's say this is XYZ coordinate, this is also XYZ coordinate, this is your transmitting antenna. So now we assume that it's propagating along the z-axis, then only it will be able to reach this receiving antenna here. So this linearly polarized antenna for the transmitting antenna is positioned at an angle theta t with respect to the x-axis, and this linearly polarized antenna for the receiving antenna is also positioned at along this direction, which is making at an angle theta r with the x-axis. So this theta t and theta r are not equal. So in that case, how much is the polarization efficiency? That's what we want to see. So now for this particular orientation of the antenna, the polarization unit vector for the transmitting antenna can be expressed as cosine of theta t x hat plus sine theta t y hat. And similarly for the receiving antenna, it can be expressed as cosine of theta r x hat plus sine of theta r y hat. So now if you want to find the polarization efficiency, you do the dot product of this unit vector for the transmitting antenna with the complex conjugate of the unit vector for the receiving antenna. You take amplitude of that, square of that, you get it. So now when you do that, what you are getting is polarization efficiency is cosine of theta t minus theta r. So cosine of theta t minus theta r, this is the angle theta t minus theta r. if transmitting antenna and receiving antennas were aligned properly, when in that case theta t is equal to theta r, in that case this will become 0. You have the maximum polarization efficiency when theta t is equal to theta r. In that case, you align the transmitting antenna and receiving antenna in the same angle. So let's summarize it. When your transmitting antenna and receiving antenna are aligned properly, that means theta t is equal to theta r. In that case, theta t minus theta r is equal to 0. Polarization efficiency is 1. Maximum efficiency you can have. But let's say if you align this transmitting antenna and receiving antenna in a perpendicular direction. So in that case, theta t and theta r are perpendicular to each other. In that case, the difference between theta t and theta r is pi by 2. So cosine will become 0 now. So that means even if you are transmitting high power signal from the transmitting antenna, if your antenna in the receiving antenna is aligned in the perpendicular direction, you won't be able to pick up any signal. So this is a very important concept you have here. If you want to have proper wireless communication between the transmitting antenna and receiving antenna, if both of them are linearly polarized, you have to align them in same angle. If you align them in perpendicular direction, you won't be able to receive any kind of signal. Similar kind of analysis you can do for CP wave antenna. If you have a CP wave antenna, let's say you position this CP wave antenna along the x-axis and it's radiating wave, CP wave antenna, array CP wave, so the omega t angle would be along the positive direction or in the anti-clockwise direction. Similarly, if you have a receiving antenna also receiving signals which are right hand circular polarized wave, so it's the wave tip of the electric field should be actually in the positive direction or in the anti-clockwise direction. So both of them are in the same polarization, RACP wave and RACP wave. And so let us consider a CP wave antenna as a transmitting antenna as well as a receiving antenna. So the receiving antenna is circular polarized, transmitting antenna is also circular polarized. If you consider both of them are of same polarization, RACP receiving antenna and RACP transmitting antenna, how much is the polarization efficiency? That's what we want to see. So the polarization unit vector for RACP wave would be 1 by root 2 of x minus jy, and for the receiving antenna also it would be 1 by root 2 of x minus jy, x hat minus jy hat. So how do we define the polarization efficiency? It's basically ET hat dot ETR hat complex conjugate square of that. So now in this case, when you find out, the polarization efficiency will turn out to be 1. So that means if you want to have a proper communication, CP circular polarized antenna at the transmitter and receiving antenna should be of same polarization. Let's say if you have a transmitting antenna which is right hand circular polarized wave and receiving antenna which is a left hand circular polarized wave, the unit vector for the right hand circular polarized wave is 1 by root 2 x hat minus jy hat. For the receiving antenna is 1 by root 2 x hat plus jy hat. So when you find out the polarization efficiency using this formula here, you'll get 0. That means if your transmitting antenna is right hand circular polarized wave and if your receiving antenna is left hand circular polarized wave, you won't be able to pick up any signal from the transmitting antenna even if you are using high power signal from the transmitter. So there is an analogy here. There's a very simple concept you have here. Let's say two persons are shaking hands. So right to right handshake is matched, but right to left handshake is not matched. So it's not possible. If you want to do handshake with another person and you are using right hand and right hand, you can do handshake. But if you are using right hand and the other person is using left hand, you won't be able to do handshake. So polarization for the transmitting antenna and receiving antenna should be same so that you can pick up the signals properly at the receiver. In that case, polarization efficiency is 1, but if you have a different polarization RACP and LACP combination, you won't be able to pick up any signal because polarization efficiency is 0 in that case. We can also consider the case where you have a transmitting antenna and receiving antenna. One is linearly polarized, another is circular polarized wave. So let's say if your receiving antenna is right hand circular polarized wave, in that case the unit polarization vector will be 1 by root 2 x hat minus jy hat, and you assume that there is a linearly polarized wave antenna at the transmitter. In that case, the unit vector for the polarization would be cos theta t x hat plus sin theta t y hat. Theta t is the angle this linearly polarized wave antenna makes with the x-axis. So let us find out the polarization efficiency for this case. You have a linear polarized wave which is positioned along theta t with respect to the x-axis, and you have a circularly polarized wave which is trying to receive the signal which has been transmitted from the linear polarized wave. So let us find out the polarization efficiency. Polarization efficiency in this case simply turns out to be half. So that means there is a 3 dB signal loss when you use linear polarized antenna as a transmitter and circular polarized antenna as a receiver. This 3 dB signal loss you cannot escape. No, it is always there when you consider linear polarized wave and a circular polarized wave as a transmitting antenna or receiving antenna or vice versa. And one more observation is that when you draw the radiation pattern of the antenna, there are two components. One is called the copolarization and another is the cross polarization component. So what is this copolarization and cross polarization? You need to clearly understand. Otherwise, when you plot it, you don't know what's going on. You have to know the concepts behind this. What is copolarization and cross polarization? So let's take one simple example. Let's say I want to measure the field of an antenna which is horizontally polarized. So the electric field is in the horizontal plane. So horizontal polarized means electric field is in the confined in the horizontal plane. But let's say, see, basically when you measure the antenna, you have two antennas. So we'll come to this later on. So let us try to understand what is copolarization and cross polarization. I will discuss it in details later on, but I will just define it now. Copolarization means you measure the antenna with another antenna in the same polarization with the antenna under test. So you will have two antennas. One is transmitting antenna, one is the receiving antenna. Usually transmitting antenna is not the one which you want to measure for the radiation pattern. Receiving antenna is usually the antenna for which you want to measure the pattern. So now if you make the measurement keeping the polarization of the transmitting antenna and receiving antenna same, then what measurement you are getting is called copolarization. In the cross polarization case, your transmitting antenna and receiving antenna will not be having same polarization. So copolarization, cross polarization means you measure the antenna with antenna oriented perpendicular to the main polarization. So the antenna for which you are using as transmitting antenna and antenna for which you are using a receiving antenna, they would be having perpendicular polarization in that case. So whatever measurements you make for the fields, in that case is cross polarization component. So example is the field of the antenna is horizontally polarized and cross polarization component will be in the vertical polarization, or if the polarization is RACP, cross polarization will be LACP. LP horizontally polarized, cross polarization will be vertical polarization. RACP, cross polarization will be LACP. Let us discuss this in a mathematical expression first. Let us try to understand this from the mathematical point of view. So if you assume a wave is propagating along the z-axis, and you can express this electric field of this antenna in the far field can be expressed in two components. One is the co-component and another is a cross component. So electric field can be expressed in co-component and cross component. Co means copolarization component, CR means cross polarization components, and you can also have unit vector for this copolarization component and cross polarization component, and wave is moving along the positive z-axis. So now when you do dot product of unit vector for the copolarization component with itself, you get 1. When you do the dot product of unit vector for the polarization, copolarization and cross polarization, you get 0. So if you want to find the co and cross polarization components of electric field, you can simply find out this is the co component, this is the cross component. So if you do dot product of electric field with the co-component, then you get the co-component of the electric field. If you want to get cross component of the electric field, you do dot product of electric field with the cross component. It will be very clear from this simple example you have here. For a linearly polarized wave along phi LP, so the angle this linearly polarized wave makes with the x-axis is called the phi LP. Let us assume that a linear polarized wave polarized along the phi LP direction. This is the angle electric field tip of the electric field makes with the x-axis. So in that case, you can write the co-component as cos of phi LP x hat plus sine of phi LP y hat. The cross component would be sine of phi LP x hat minus cos of phi LP y hat. So now when you do dot product of these two, you will get 0. When you do dot product of this with itself, you get 1. Dot product of with this itself, you get 1. But cross dot product, you will get 0. So you can easily verify that it's a dot product of this and complex conjugate of this. You get 0. Let us make major simplification here. If you consider this linearly polarized wave is polarized along the x-axis, in that case phi LP turns out to be 0. The angle this tip of the electric field max with the x-axis will become 0 now. In that case, this term here will become simply u co-component will be x hat, u cross component will be minus y hat. You can just put it phi LP is equal to 0 in this previous expression. U co-component will be x hat, u cross component will be minus y hat. So if you want to get component of the electric field along the co direction, just do the cross product with the u co, and cross component you do dot product with the cross component, then you get the cross component of the electric field. In this particular case, E co will simply become Ex, E cross will become minus Ey. Similarly, if you consider the y directed LP wave, phi LP will become 90 degree now. In that case, U co component will be y hat and U cross component will be x hat. So if you want to find E co component, you do dot product of electric field with the U co complex conjugate unit vector of that. What you get is Ey. E cross will become Ex. Similarly, if you want to find E co and E cross for the right hand circular polarized wave, so if you consider a right hand circular polarized wave along and propagating along the z axis, U co component will be x minus x hat minus j y hat divided by root 2. U cross component will be x hat unit vector along the cross component would be x hat plus j y hat square root of 2. This is the unit vector for the right hand circular polarized wave. This is the unit vector for the left hand circular polarized wave. This is the co-component, this is the cross component. Now you do the dot product with electric field vector, what you get is Ex plus j Ey square root of 2. This is the E co component. E cross component will become now simply you do the dot product electric field with the cross component Ex minus j Ey divided by root 2. Similarly, if you want to find the elliptically polarized wave cross component and co-component unit vector would be x hat plus a exponential j phi e p y hat divided by square root of 1 plus a square. A is the amplitude of the y component of the wave. Phase is given by exponential j phi e p. For the cross component of the wave, you can find out it will be minus a exponential j phi exponential minus j phi e p x hat plus y hat square root of divided by square root of 1 plus a square. When you do dot product of these two, you should be getting 0. When you do dot product of this with itself, you should be getting 1. When you do dot product this with itself, you will be getting 1. So how do we measure this co and cross component? That's what we are going to see in the next diagram. So basically, as I have already told you, you have a transmitting antenna and you have a receiving antenna. So this is a transmitting antenna, which is a horn antenna. You have a receiving antenna. In this case, it's a microstrip antenna. So now this is fixed. Transmitting antenna is usually fixed. Antenna under test, AUT is possible to move in any arbitrary direction by using a motor. You can move this. This is fixed, but this you can keep on moving. So you move this AUT antenna under test in two principal plane. One is elevation plane, another is azimuthal plane, to find out E plane and H plane of the radiation pattern of the antenna. Then the received field strength is measured by a spectrum analyzer or power meter, and from there you can generate the radiation pattern of the antenna in the two principal planes, E and H plane. From the E and H plane pattern you can generate the 3D radiation pattern by rotating one of them along the pattern of the other plane. So let's consider a Hertz dipole, and I want to find out the E plane copolar measurements and cross polar measurement. So what is the polarization of a Hertz dipole? Hertz dipole is vertically polarized. So Hertz dipole is vertically polarized. So now if you position your Hertz dipole along the z-axis, for the copole measurement you have to align this receiving antenna also in the same plane or in the same direction. So this is the antenna under test. You have a transmitting antenna which is aligned along the z-axis. Let's assume that this is also Hertz dipole, this is also Hertz dipole for easier illustration. So now if this Hertz dipole and this Hertz dipole, if they are aligned in the same direction, then we are making the copolar measurement. So and after that you want to have a E plane copolar measurements, you move this Hertz dipole in this circle, no? In this circle you move it. So now in that case, so this Hertz dipole is sending out signal and this Hertz dipole is capturing the signal. You move it in this XZ plane. Then what plane is this? This is the elevation plane. So you measure the change in the received electric field from this transmitting antenna by this receiving antenna in the XZ plane. So this is the elevation pattern measurement of the antenna, and this is copolar because you have aligned this transmitting antenna and receiving antenna in the same polarization. If you want to make cross polar measurements, what you can do is you can just keep this transmitting antenna in the perpendicular to the receiving antenna. So this transmitting antenna and receiving antenna, they are not in the same plane now. So this transmitting antenna is directed along the y-axis, but receiving antenna is directed along the z-axis, so they are perpendicular to each other. So in this case you keep the transmitting antenna in this direction and receiving antenna in this direction, and you move this receiving antenna in this circle and try to find out the fields which has been received by this antenna by using a power meter or a spectrum analyzer. Then you plot it with respect to theta, then you get the elevation pattern of the antenna in the cross polar case, for the cross polar case. So this is the E plane cross polar measurement of the antenna. You can also make measurement for the H plane. So for the H plane, what do you do? For the H plane measurement, if you want to make the copolar measurements, you keep this antenna and antenna, transmitting antenna and receiving antenna in the same direction. They are aligned properly so that they are in the same polarization now. This antenna and this antenna, they are aligned in the same direction, so they are in the same polarization now. What you do is you move this test antenna AUT, antenna under test, in the XY plane. So in that case you will be able to receive signal transmitted from the transmitting antenna in the XY plane for different values of phi. So you can get the azimuthal pattern of the antenna, and this is for the copolar case. You can also make the cross polar measurement. In that case you align this transmitting antenna and receiving antenna in the perpendicular planes. So this is aligned along the y-axis, this aligned along the z-axis. They are not in the same polarization now, they are in the cross polar case. So this measurement, what you do, you align this antenna along the y-axis and you align this antenna along the z-axis, and you move this antenna in the xy plane and try to receive the signal which has been transmitted from this antenna. And whatever signal you receive for different values of phi, you plot it by measuring with a power meter or a spectrum analyzer. You get the H plane cross polar measurement pattern of the antenna. This is a typical radiation pattern of the antenna we have measured in our lab. This is a copolar component. Solid lines are for the simulated one using isophysis. Dashed lines are measured using the setup we have in the lab. So you can see that the simulated and measured results are very close. This for the copolar case. For the cross polar case, what you observe is gas line and solid lines are very close, and moreover you can observe that copolar, you have the fields which are very high for the copolar case. Cross polar fields are very low, and it's very good to have very low level of the cross polar component, because this is actually wastage. We want to send signal in the copolar direction, but cross polar, whatever signal has gone to cross polar case, is a waste of energy and power. So now you can see that if you consider this is 0 dB, the cross polar component is around minus 15 dB, minus 50 dB. So the cross polar component is very low with respect to the copolar component. You can also see the simulated and measured results of the one of the antennas we fabricated in our lab and measured in our lab. So what you see is dash line is for the measured one and solid lines for the simulated one using the SFSS, and they're matching quite closely, and you see that copolar component in the H plane is very high, and relatively the cross polar components around minus 60 dB down. This is a very good pattern we have. We can also look at the antenna input characteristics. Antenna is actually connected to a transmission line. All the wires are replaced by transmission line at the microwave frequency, high frequency. So antenna is put at the end of the transmission line. So you can assume this antenna is a load to the transmission line, and you can find out the equivalent circuit of the antenna. Simplest model people usually use for resonating antenna is series RLC resonator. So this equivalent circuit for the antenna is going to change for different types of antenna. So the simplest model we can consider for an antenna which is resonating is series RLC resonator. In the series RLC resonator, you have inductance, capacitance, and inductance and capacitance will give you the resonance frequency, and you also have losses. Here you have two kind of radiation. One is called you have two kind of resistance. One is due to the radiation and one is due to the loss. Radiation resistance will actually give you the radiated power. These losses are due to the conductor losses or dielectric losses, because we make most of the antenna using either conductor or dielectric. And once you have the quality factor of the antenna, you can also find out the fractional bandwidth of the antenna. The quality factor, you take the inverse of that, you get the fractional bandwidth of the antenna. So bandwidth can be found out from the quality factor. This is a 3 dB bandwidth. What is quality factor? Quality factor is defined as omega 0. Omega 0 is 2 pi f0. F0 is the resonant frequency times the energy stored over the power radiated and ohmic losses. So here you have inductor and capacitor. There will be magnetic energy storage and in the capacitive energy storage, electric energy storage. So you can find out the energy storage due to inductor can be given like 1 by 4 I square L, and energy stored due to the capacitor can be given as 1 by 4 I square 1 by 2 pi f0 whole square L. This due to the capacitor, no? So omega 0, you multiply omega 0 with the energy storage divided by the power loss. Power loss can be either in terms of radiation loss or from the losses due to the ohmic losses. So here you have two kind of resistor. One is due to the radiation and one is due to the losses. So that power can be calculated as half I square RR plus RL. RL is due to the losses, RR is due to the radiation. So you simplify it, simply what you get is 2 pi f0 L by RR plus RL. So you can make a modification, write it in this form also, and similarly you can simplify it further and write this of the form 1 by omega 0 RRC then RR divided by RR plus RL. This term here looks like radiation efficiency, because RR is the radiated, dependent on the radiated power, is the radiation resistance. This is due to the losses. So RR divided by RR plus RL is basically equal to efficiency of the antenna, and this is 1 by omega 0 RRC is your quality factor for the lossless antenna. So the quality factor of antenna can be expressed as quality factor for the lossless case multiplied by the efficiency of the antenna. Lossless case, you don't have any losses, RL will become 0, then in that case Q will become Q lossless, efficiency will become 1. So the radiation efficiency of antenna is defined as ratio of the power delivered, how much power is radiated, then how much is the total power input to the antenna. So you can define it as half I square RR. This is the total radiated power, and this is the total power, half I square RR plus RL. You have considered losses also. When you cut out the common term, what you get is radiation of the efficiency of antenna. For this simple model you have is RR divided by RR plus RL. Usually all the coaxial cables, all the waveguides, all the transmission lines are manufactured for 50 ohm. And at the end of the transmission line you connect the antenna. So antenna can be actually modeled as a load to the transmission line, and if you find out the impedance of the antenna, we'll code this as a ZL, load of the transmission line. So if impedance of the antenna is find out as ZL, you can find out reflection coefficient as ZL minus Z0 divided by ZL plus Z0. Z0 is the characteristic impedance of the transmission line. ZL is the impedance of the antenna. From there you can find out how much is the signal reflected back to the source when you put antenna at the end of the transmission line. So once you have the reflection coefficient, you can also find voltage standing wave ratio is simply 1 plus modulus of gamma minus 1 minus modulus of gamma. So now this reflection coefficient, the maximum reflection you can have is 1. So incident signal is having amplitude of 1, the maximum it can reflect is 1, the minimum it can reflect is 0. So the value of gamma is between 0 to 1, and similarly from here voltage standing wave ratio is the ratio of the standing wave B max divided by B min, maximum standing wave divided by the minimum standing wave. So voltage standing wave ratio will be having a value of 1 to infinity, because when you have gamma is equal to 0, the BSWR is 1. That means gamma is 0 means all the signal which has been sent from the source will be radiated by the antenna. There won't be any reflection. In that case BSWR is 1. We have maximum reflection when gamma becomes 1, this BSWR becomes infinity. So the range of values of gamma is between 0 to 1, and for BSWR is from 1 to infinity. So there is a very important parameter for the antennas which we usually define antennas bandwidth. Antennas bandwidth is defined as the frequency range over which BSWR is less than or equal to 2. That means voltage standing wave ratio should be less than or equal to 2 within the bandwidth of the operating bandwidth of the antenna. So this will be very clear from the next diagram here. So here we have plotted gamma with respect to frequency, reflection coefficient in dB with respect to frequency. When BSWR is 2, you can find out gamma. Gamma will be approximately minus 10 dB. So the bandwidth of the antenna is defined as this bandwidth. So for example, let's consider measured one. This is the simulated one, and measured one. Simulated one is a reflection coefficient for the antenna using HFSS simulator, and measured one is measured in our lab. There's line here. They are almost following each other, all very close. So let us consider this measured reflection coefficient of the antenna in dB with respect to frequency. So as I have told you, the bandwidth of the antenna is defined for BSWR less than or equal to 2. When BSWR is equal to 2, you can find out gamma, and gamma in dB will be around minus 10 dB. If you are having a value of gamma less than minus 10 dB, you are within the operating bandwidth of the antenna. So let's look at this frequency here. Minus 10 dB frequency here we usually call as F high, and minus 10 dB frequency here will be F low. So this range here from F high to F low is the bandwidth of the antenna. So if you define percentage bandwidth of the antenna as F high minus F low divided by the center frequency Fc, the resonant frequency of the antenna. F high minus F low divided by Fc, you get the fractional bandwidth. So you multiply by 100%, you get the percentage bandwidth of the antenna. That's how you define the bandwidth of the antenna. Thank you very much. This is all we have in this class.